So the next thing to do is to find f of x and t as a plane, because in this little area right around the point x prime t prime, it actually can be approximated as a plane. So question is how to do this. So basically you draw this, do this as t, and this is x, and then this is f of x and t, and f of x and t is some kind of slope. So this is some kind of shape, and then there's going to be a little plane here. And this plane basically surrounds the point going downhill, x prime, t prime. So this is the only area that's going to be relevant to the derivative, that it is affected by the boundary, the derivative with respect to time. So basically, for a small area, around x prime and t prime, f of x comma t can be approximated not sure if there's really supposed to be two p's in that or not, as a flat plane. Okay, and this is basically implied by the concept that this function is reasonably well behaved. So long as it's reasonably smooth and it's differentiable and it's continuous, it should be approximable by a plane. If it's not if it can't be approximated by a plane over small areas, then this equation isn't going to work anyway. So the next part is to figure out what the equation of the plane actually is. So to do this, I'm going to make a definition. I'm going to define z as the function of x and t. And this, of course, implies that f of x comma t minus z is going to equal 0. So the next idea is to find the normal vector to the plane. So basically we need to know what this normal is that points out away from that point x prime t prime that's in the box. And there's a way this is defined to do this, and it basically says that the normal vector of a function can be essentially derived using its gradient. So this normal vector and vector is going to equal the gradient of this, the function of x comma t minus z. And this in turn equals change in f with respect to x, the partial derivative of the function with respect to x. I'm going to start dropping these variables for the moment otherwise the notation gets really long. So the next is the function of f with respect to t hat, and then the negative of the z hat. So that's a normal vector. And in order to do this computation to get the equation of the plane, there needs to be one other vector. So this is going to be, by definition, this vector that originates at the point x prime, t prime, effectively z prime. So define a vector R, and this starts at x prime, comma t prime, comma f of x prime, comma t prime. So this is effectively, the vector is going to start effectively right there. So the plane is going to be essentially every vector R which is going to satisfy a special equation. So for a plane, for the points to be in a plane, basically by definition, all vector dot n hat vector is going to equal 0 if the end of all at the end that's the, okay, so only if the y and z of all lie in the plane. And all is going to, the definition of all written out fully is basically all equals just x, the arbitrary location, x prime plus t minus t prime, and this is x hat, this is t hat, plus z minus the functional value at x prime and t prime, z hat. So go ahead and finish the equation. So then to use this, so if the x, y, and z of these, which means this, that, and that, lie in the plane, then this will hold. So by applying this equation, this will give an equation for x, not y, actually x, t, and z. That will go ahead and fix x, t, and z in the plane. So this becomes all hat dot n hat becomes x minus x prime, change in f, partial with respect to x, plus t minus t prime, and change in f with respect to t, plus f of x prime, comma t prime, minus z, this will equal 0. So going to basically solve for z, which is, so remember that z was defined as f of x comma t. So to find x comma t, basically take this guy, minus x prime, change in f, x plus t minus t prime, change in f, change in t, and then add the constant, which is f x prime comma t prime, and have it equal z, which would be on the other side of the equation, except z is f of x at t, so this equals f of x at t. So this is the way of converting f of x at t to what's actually a plane. And there's one more point here. The derivative of f of dx, actually, each of these derivatives, for instance, let's do df is actually f evaluated at x prime and t prime, because this is actually the df dx, which is the df dx for determining the normal vector, and the normal vector comes out from the middle of this little box. So it's fully determined by t prime, which basically determines x prime, gives the normal vector. And the same thing goes for df dt is df t evaluated at t prime. So basically, and could also put the x prime there, but I'm not going to write both the x prime and the t prime out. So these guys are evaluated at t prime, and this is evaluated at t prime. So what's important about this equation is that much of this is actually a constant. So for this equation, I'm going to write the constants in blue. I think I'll also write the outside in blue. So I'm going to do this. So this and the derivative, which is evaluated at a fixed point t prime, x prime. This is actually a constant, so of course it's x prime. And doing this, t prime is a constant. The derivative with respect to t, evaluated at t prime, is a constant. This function of x prime comma t prime, that's a constant. So the stuff that actually changes, there's an x. Probably make this a little bit. So there's x is not a constant, and t is not a constant. So these are variables, but pretty much everything else is a constant. So only that and that are variables. So the idea is to basically solve this thing, which is the integral of the function x and t dx. With the need to hold on a second. The derivative of this integral d by dt of this function of x and t dx with a variable boundary, using the assumption that this integral is extremely small. So the idea is to basically approximate this thing using a flat plane. So f of x and t becomes this flat plane that looks like this. And this flat plane, of course, only depends on x and t. The rest of these variables are constants that are determined by the properties of f at the point t prime, x prime. So basically this needs to be substituted into that, which involves a fair amount of algebra. So starting here, so this is d by dt. Just rewriting this equation, b naught of t and the function of x comma t dx. And it will be approximately, since this is a plane approximation, there's d by dt and then the integral b naught to b t, and then there's going to be bounds. Let's go bounds, so this is x minus x prime, the derivative of f with respect to x, which is a constant valued at t prime, plus t minus t prime, and the value would be f with respect to t, which is a constant valued at t prime, plus f evaluated at t prime, which is yet another constant. Okay. And then this is dx. Okay, so the next step is just a fair amount of algebra, which I'm going to skip. There's a few tricks to it. One of the tricks is to do this. There's a point where there's this type of integral, b naught to b of t, and then there's time, which is available, df, which with respect to dt evaluated at prime, which is a constant, dx. And since this is just a constant, this is dx. Since this is integrated over x and not t, the t can actually move out of the integral without this being a problem. So this ends up being the b of t, and then df t about t naught. And this is just a constant, and there will be a lot of these constant intervals, and the way the constant intervals work out is always the same thing. So the t is out front, and then this entire integral part ends up being the constant. Here's the f with respect to dt, evaluated. This isn't t prime, this t0, that's actually t prime. Prime. And then on the inside, there's just b of t minus b naught. So we know there's a constant interval that just ends up being integrating. If this was moved out, this would just be 1, so that would integrate to x. And x would turn into b of t, and then minus b naught. So this integral looks like that. There's a lot of integrals of the form like that. So with the entire thing worked out, what comes out is basically this thing basically is going to equal, this guy will equal, so df with respect to dx evaluated at t prime, and then here's the b, one of these b of t's minus x prime, and then d of b t with respect to dt d of f with respect to dt evaluated at t prime, and another one of these terms, b of t minus b naught this time, and plus derivative of f t evaluated at t prime, and then this is t minus t prime, and then this is a derivative of b t dt, and then plus derivative of b of t t, and then this function f evaluated at t prime. Okay. So what happens here is there's a lot of these terms like this, and what it turns out is these terms, most of these terms actually go to 0. So since the derivative can take place in a arbitrarily small state, the time difference can be made to basically go to 0. And if the time difference goes to 0, then it basically forces the difference in space, which is the x difference, also to go to 0. So this implies basically we have, so basically what happens is so furthermore, basically t naught is less than or equal to t is on this entire range is greater than or equal to t naught, and it's going to be less than or equal to t naught plus delta. And for x, there's a similar equation. There's b naught, so x is going to be greater than or equal to b naught, and it's going to be less than or equal to b naught plus big delta. And of course, x equals b of t. So by definition, here x is on the boundary. Okay. So, basically, this implies that, so these equations basically imply that B of t is basically going to go towards x prime. Since x prime is basically going to have to approach, it's basically going to get squished, so B of t. So x is somewhere in here. So wherever x prime is, as this gets smaller and smaller and smaller, x is basically going to get squished towards b naught, which means b of t is basically going to get squished towards x prime, and x prime is going to get squished towards b of t. And boundary condition of t is going to go to b naught. And t is basically going to go to t prime. So, which means basically, what this means is unless these functions, df, dx, are valued at t prime, df, dt, and or db, the function of t at dt, valued at t prime, which goes, so what happens with these guys going through, all of these guys basically approaching each other, what this actually does collectively is this will imply that B, let's actually use a different color to make this a little cool. So this guy will basically imply that these guys, BT minus x prime, BT minus B naught, and T minus T prime, these are all going to go to 0. As these things basically get squished together, all of these guys are going to go to 0. So long as these guys do not blow up, all of this term is basically going to go to 0. So this is going to 0, this is going to 0, and this is going to 0. So the only thing that would prevent this entire term from going to 0 is if this or this or that basically increased so much that it contradicted the limit. So unless these guys 0, what basically happens is all of these terms are going to go to 0. So df dx and b of t minus x prime, and then db t plus df dt, and then this is b of t minus b naught, and then added to it is df dt, this is t minus t prime, and this is db dt. This thing is basically going to go to 0. Check that I basically put down all these terms. So with all of that going to 0, which is basically all of this just went to 0, the only remaining term is going to be this guy. So what it turns out is this is the only term that actually matters. So this is dB with respect to t, dt. And it's going to basically be evaluated at t prime times f evaluated at x prime, comma t prime. And then basically use the fact that x prime equals b of t prime, basically by definition. So another way of writing this is basically to write it as f of b as a function of t, comma t, and then dB as a function of t, dt, and this whole thing is evaluated at t equals t prime. And this equals basically what we had at the beginning, this guy. So that actually equals the integral that's being differentiated. So this guy equals I dt of the integral b naught to bt, whatever it's approximately, essentially equals, because in the very small space that the derivative operates on, this ultimately this limit converges to what it's supposed to be. So d by dt, this is f x comma t dx. So far it has been established that the derivative with respect to t with the fixed boundaries of the function of x and t dx equals the same integral with the fixed boundaries with the partial derivative inside the integral. So d by dt partial with respect to f, x, and t, and then integrated. And this is evaluated at time t prime. For the moving boundary, this integral can be taken on a very small area, very close to where the boundary actually is at t prime. And on this area, by using the plane approximation, it can be shown that the d by dt of this function with the moving boundary equals the function evaluated at b t prime and t prime, and then the derivative of b with respect to t also evaluated at t prime. So for the entire equation that's written out, this is basically going to say d by dt, just combining these boundaries, d by dt of a to b of t of f of x comma t dx is going to equal these two equations, which is going to be, the first one is going to be, since b naught basically approximates b of t prime as it gets closer and closer in the limit, this is going to be a of b of t with the partial derivative f comma t dx, and then added to it is going to be the function of the boundary for the x and t, and then the derivative of the boundary with respect to time. And this, of course, is all evaluated at t equals t prime. And the same thing for this. This is evaluated at t equals t prime. So that is the case for one boundary moving. If both boundaries move, it turns out it's about the same equation. So what it actually looks like is d by dt and an integral between at and bt. This is a function of x comma t dx, and this thing equals first part and then the partial derivative, the function of x and t dx, and then added to that is what came before, still f of b of t comma t db with respect to dt. And then in this case, the boundary, if the boundary moves forward, it's actually reducing the area inside the integral. So this is actually a negative. And this turns out to be the function of a of t. And this could be derived in as pretty much exactly the same way as the other boundary conditions is derived. The only thing that's going to change is the sign. ODA is a function of t. So that's basically the 1D Leibniz equation. So to look at this further, see if I'm able to find the correct slide. So basically this is the graph. And what it basically shows is there's, okay, good. So basically this is the integral, the partial derivative of the function. It's basically taking into account this area here. So this is basically the graph of the function in x coordinate and time, starting at time 0. And then a short time later, the function has changed its location. So that change in location of the function, the change in the shape of the function with respect to time in the body of the function is accounted for by this integral. And then there's these two things at the end. So at the end, what it basically says is the value of the function basically here, the primary value, which starts here, function at a of t. So this would be basically a of t naught. And this would be b of t naught that starts here, can be extended across, and then it's multiplied by this width, and that basically depends on how fast the boundary is moving. So the boundary is moving at db dt, so db dt times delta is going to be this distance here. And so that distance times the location of here basically gives the area in here, and this dark area, as well as this area that's caused by the combination of the two terms, is basically just ignored, because this is basically a small distance, and this is also a small distance, so this is a second order effect. So in the limit, this area right here pretty much goes away, and this area right here goes away. So it's possible to just approximate the function by its value at t0, instead of having to go ahead and actually take into account what's going on in there. So this is basically the 1D Leibniz equation. So it's going to be, so this is the 1D. Let's make that thicker. So this is the 1D Leibniz. Rule. There it goes. Okay. So the next topic will be basically taking the 1D and extending the 1D Leibniz to the 2D case.